We would now like to talk about the same sort of problem as in the last video about the motion of a mass on a spring, a vibrating system, only now we'll put in some sort of damping. This would normally come from friction in the system, and of course in any real vibrating system there will be friction. Remember when we had the differential equation mu double prime plus ku equals 0, this was assuming that the only force acting on the object came from the spring. This was the force that came from Hooke's law. But now if there's a second force, we still have Hooke's law, a force from the spring, which is minus k times u. But now we'll have some sort of friction force. And in general, at least for small velocities, the friction is typically a constant, which we'll call gamma, times the velocity. And again, by convention, gamma here will be the friction constant. Gamma will be positive, and this force will be minus gamma times the velocity u prime, because if you have an object moving, say, to the right, the friction force will be inhibiting that, which will be a force pushing back to the left, and vice versa. The force will be opposite the direction of motion. So in all of these, remember here, k is greater than 0, and gamma is greater than 0, and of course the mass m must be positive as well. When we incorporate that into our equation, we have m times u double prime, that's the mass times the acceleration. That should be the sum of the forces. If we had these two things on the other side, you would see that would be minus gamma u prime minus k times u. We're putting them over here just to make the differential equation into standard form. We get this differential equation for modeling a damped vibrating system. This is still a second-order linear, homogeneous, constant coefficient differential equation, and it's still one that we can solve really nicely. It has characteristic equation now, mr squared plus gamma r plus k. Remember, all of these three constants are positive, and we can just use the quadratic formula and say that the solutions r is just minus gamma plus or minus the square root of gamma squared minus 4mk all over 2m. It's going to be very important what the discriminant gamma squared minus 4mk looks like. We'll worry about that in a second. Before we do, just if you factor out a gamma over 2m, you can write it as the solutions r1 and r2, or gamma over 2m times minus 1 plus or minus the square root of 1 minus 4km over gamma squared. Again, we have to interpret this. If this discriminant is negative, interpret the square root of that negative number as I times the square root of the absolute value of that negative number. But these are the solutions given that interpretation. Now, there'll be three possible situations. The first one we'll call overdamped, and we'll see in a minute why. That's when the discriminant gamma squared minus 4mk is positive. The second will be critically damped. That's when the discriminant gamma squared minus 4mk is equal to 0. And the third one is underdamped. Gamma squared minus 4mk is negative. You'll see, first of all, if gamma is big, that means the friction force is very large. That will cause us to be in this overdamped situation. For a fixed mass and fixed spring, more friction will put us in the overdamped situation. There'll be some critical value of gamma that puts us in the critically damped situation. And if gamma is very small, we'll be in this underdamped situation. What do things look like in this overdamped situation? Well, as we wrote down before, we'll have R1 is gamma over 2m, now times minus 1, plus the square root of 1 minus gamma squared over 4m. Actually, I lost this 4km over gamma squared. This is Let me fix that. And R2 will be gamma over 2m times minus 1 minus the square root of 1 minus 4km over gamma squared. Here's the first thing to notice. In this situation, when the discriminant was positive, this is a positive number. And notice that this positive number here is less than 1. So minus 1 plus that is still negative. In other words, R1 is negative. And in fact, R2 is even smaller than R1, because here you have negative 1 and you're subtracting a number, making this now even less than negative 1. So you have R2 less than R1 less than 0. And what do our solutions look like? Well, I'll just write down the general solution. It would be u of t is some constant c1 times e to the r1t plus c2 e to the r2t. And remember, both of these are negative. So what does that look like? These exponential functions both go to 0 very quickly. The e to the rt goes to 0 more quickly, so kind of the long-term behavior, both are tending to 0, and the e to the r1t dies out a little more slowly, and you can have some, depending on the initial condition, possibly some initial bump behavior, but basically it just dies out pretty quickly. So the damping in our mass spring system changes from the undamped situation, where we just had oscillatory behavior back and forth, which would go on and on and on forever with the same amplitude, to a situation, this overdamped situation, where you pull the spring out, you let it go, and whoop, goes right back down towards 0, heads right back, overdamped, meaning you don't get any oscillations here whatsoever. What does it look like in the critically damped situation? Well, in this situation here, gamma squared minus 4km equals 0. This was the discriminant in the characteristic equation. That means you have solutions, or one solution, to mr squared plus gamma r plus k equals 0. That solution is r equals just minus gamma over 2m, a negative number, and that means your general solution to the original differential equation is u of t is some constant c1 times e to the rt. Of course, here you can see r is a negative number, plus c2 times t e to the rt, because we have a repeated root of this characteristic equation. And if we graph that, it wouldn't look substantially different from the overdamped situation. These both go, the e to the rt goes to 0 very quickly. Even though t blows up, e to the rt goes to 0 much more quickly than t increases. So you could have a situation like this. You might have it crossing the axis once, because you can write this as c1 plus c2t times e to the rt. So this might be 0 at most once, but all the solutions would just head to 0 very quickly. No real oscillations, even though it can cross the t-axis. There's t, and this is our u. It could cross the t-axis, but no oscillatory behavior whatsoever. Finally, let's look at the underdamped situation. In this situation, again, the characteristic equation was mr squared plus gamma r plus k equals 0. We had the solutions, which I'll right now, since we can say the discriminant gamma squared minus 4km was negative, we can write the solutions as R1 is gamma over 2m times minus 1 plus I times the square root of, and now it will be 4km over gamma squared minus 1, and R2 will be gamma over 2m times minus 1 minus I times the square root of 4km over gamma squared minus 1. We can now let mu be the imaginary part of these roots R1 and R2. That will be gamma over 2m times this square root, which will be precisely the square root of 4km minus gamma squared all over 2m. And then we can write R1 and R2 just as minus gamma over 2m plus I mu and minus gamma over 2m minus I mu. Then we have solutions to the differential equation of e to the minus gamma over 2mt times cosine of mu t and e to the minus gamma over 2mt times sine of mu t. And then of course the general solution would be u of t equals e to the minus gamma over 2m times t times a constant c1 cosine of mu t plus c2 sine of mu t. Again, we can combine this linear combination of cosine mu t and sine of mu t into a single cosine wave, r cosine of mu t minus delta. R will be, well, mu will be what we call the quasi-frequency. We're talking about angular frequency here. We call it the quasi-frequency because cosine of mu t minus delta will be a single cosine wave with period 2 pi over mu. So it would be the frequency for that function. But the whole function u of t is not periodic because it has the amplitude r multiplied by e to the minus gamma over 2m times t, which dies down pretty quickly as t goes to infinity. So what do these solutions look like? Let's try to draw a picture here. If we just had r cosine mu t minus delta, it would be just like the undamped situation where we'd have a cosine wave going up and down, oscillating forever. But we're multiplying it by e to the minus gamma over 2m times t. That would be a very quickly decreasing exponential function. I'm going to draw it here above and below because what actually happens is you have this cosine wave whose amplitude is r times this function, so it will kind of go up and down between these things. Here's u, here's t. This is u equals e to the minus gamma over 2m times t, and here's u equals minus, I won't write it, u equals minus e to the minus gamma over 2m times t, and you'll see then the solution will oscillate back and forth, but with an amplitude that quickly dies down towards 0. So in the underdamped situation, you will get continued oscillations, but those oscillations just die down.